Yeah, that too. Anyway, I'm talking a little too much. Class is starting.
All right, happy Monday. We're into week 4, which is exciting. We have an exam this Friday. How do we feel about reviewing for that? What day would we like to start reviewing for that exam? Have we had a chance to look at the study guide and get a sense of what we are familiar with, less familiar with, would like some extra practice with? How do we feel?
To be honest,
Yeah.
uh, yeah, a decent amount of it I'm semi-familiar with. I haven't exactly done a ton of studying along with the homework assignment I've been busting my butt on. But yeah, a decent amount of this I'm reasonably familiar with. I think I am going to try practicing, but
Wednesday? That was going to be my default. If people didn't have an opinion, is let's start with Wednesday and see how that goes and whether people would like an additional class period.
yeah, I'm actually in agreement.
Okay, I will.
I was actually going to
Put that on
suggest
the
that
books.
anyway, so
All right, we'll put Wednesday on the books as our first study session. I won't necessarily have a ton of material prepared for these kinds of review sessions. So if you would like particular practice problems, like I would like a practice problem over this material, then let me know at least 24 hours in advance so that I can find some problems that I want to go over that I think are relatively similar in difficulty or style to what I would throw on the exam. Otherwise, I will be relying on people's questions on the day of, and I can gladly tackle whatever questions you have on the day of the review. But again, if you'd like an on-the-spot practice, the material for that will come from your suggestions in advance. I can try to find something the day of, but it will take me a good amount of time to do. And that probably isn't the best way to spend the actual review time.
definitely. Actually, my own suggestion. I'm not entirely sure how much practice we're gonna need, but maybe as plan B, you can just do some searching up on a ton of problems on the study guide, at least one per set of stuff we're trying to review just in case. Just my own suggestion. I'm not going to force anything.
I want to focus on what the class feels like is a weakness where I can. And if I get 3 requests for one thing and 1 request for another, then I will try to weight the problems in level of demand.
All right. Well, and just trying to help.
Oh, yeah, absolutely. I will be prepared one way or the other. It's just a matter of what the class needs.
All right.
All right, questions before we dive back into dynamic programming? We have an assignment due on Wednesday. I'll have office hours starting right after class for a couple of hours. Happy to help people get started or get unstuck if you've gotten started and stuck. All right, back into dynamic programming we go. So on Friday, we motivated the concept of dynamic programming by looking at both a top-down and bottom-up view of the Fibonacci sequence. And what we saw was if we have a bottom-up approach, as we would if we wrote this iteratively, it was very easy. But we had to start at the Fibonacci of 0 and 1 and calculate the next until we reached our target. But if we had a top-down approach, there were some considerations we needed to think through. And we found that if we just brute forced this without really thinking about it, we ended up with an exponential number of subproblems. And that was going to take significantly longer than the bottom-up linear time that we took when we started from the base cases and worked up. If we intelligently stored our subproblems as we did this, then it wouldn't take any significant longer period of time than it would have doing this bottom-up. We just had to intelligently store the subproblems so that it turned into kind of the bottom-up process, but from a top-down perspective, if that makes sense. So Fibonacci was very interesting to see. I love using this as an example for that, because it really motivates the difference between intelligently writing an algorithm where you recognize those subproblems and just implementing something that you think will work. we started talking about the general dynamic programming steps. I just wanted to quickly review these. And so if we started this entire quarter talking about divide and conquer, and very frequently divide and conquer style of problems are dynamic programming in nature when those subproblems do share components. So it's less so in the algorithms that we motivated. A lot of our searches don't share subproblems. Merge sort is always breaking down into a new subarray before there are no repeated subproblems in merge sort, so we don't need dynamic programming for it. But there are many cases where we find that those subproblems do have overlap. So if we're looking at the problem and breaking it down, this is very much just like a divide and conquer style of approach, thinking about what is the structure of an optimal solution, how do the problems break down, what is the optimal solution in terms of a recursive process. Then we can compute the value of the optimal solution in bottom-up fashion, and then construct the optimal solution from their computed information. And we need step 4, because we end up needing to be able to reconstruct the path that we've taken. We'll see this when we dive into the second example that I'm going to show, that you frequently end up with a result that gives you a score or an optimal value, but doesn't tell you the process we used to arrive at that value. So as we are computing, we need to store something like a backtracking pointer that allows us to, when we reach the solution, be able to trace back and say, what subproblem did we get this problem from? And based on the nature of those subproblems, we'll be able to find the path back to the beginning so that we can reconstruct the solution. And maybe I'll motivate this by introducing the example that we're going to go over and then talk about that a little bit before we dive into our intro example. So if we're looking at sequence alignment, which is what we're going to go look at, this is DNA sequence alignment. We're looking at how related two strands of DNA are to each other. And there are ways to do this. The brute force number of ways to look through this is we compare every substring to every other substring. And there are an exponential number of those substrings. So if we're doing this in brute force, this is going to take forever. But we can ask a question about the current state based on where this could have come from. So if we are in the process of aligning, I don't know, CAT, some more stuff, to GCA and some more stuff, then by the time we're at the query, how does A map to T? There are 3 ways this could have come from. It could have been the optimal solution of anything back in any of these 3 places. So here's our query. I'm going to leave that as a question mark. And it could have come from 3 prior subproblems. The optimal way of aligning CAT with GC is going to be where this point is and that calculation. So if we take however the best way to align that is, plus adding a gap as we move down, so you're basically aligning CAT with GC gap, then we find that there is a potential score for this optimal problem. Similarly, we could align GCA with CA gap and add that gap in, and that gives us another way to reconstruct the solution. We can also look at the optimal way to align CA with GC, that puts us here, and then matching A to T or mismatching A to T is a third way that we could create an optimal solution to this alignment. But we don't have to, at this stage, look more than that. There are no other ways to align these 3 sequences than looking at the already existent subproblems and the solutions that we would have calculated in a prior step of this process. So we start with some base cases and we start filling out each of these cells. And the way we're going to do this is look at the structure and say that this problem is either built from this subproblem and a gap, this subproblem and a gap, or this subproblem and a match or mismatch of these 2 characters. And we can come up with an optimal alignment of these 2 structures from just analyzing the solutions to the subproblems. And again, without having to think through the exponential number of subproblems. I'm sure this doesn't make a ton of sense at the moment. I'll introduce the algorithm and the reasoning for it, but the idea is rather than looking at every possible solution, we look at just the subset of solutions we already have plus some process to get us to this solution. So what is the optimal substructure of the problem? That's what this slide is trying to get at. So we don't need to do that if we only care about the value. How related are they? And not that we want to reconstruct a solution of what is the alignment of the sequences. Rather than doing this all at the end, we're doing it incrementally as we figure out for this subproblem, here is the optimal substructure. Then we put the backtrace arrow at that stage. Again, we'll see this in a lot more detail when I actually run through a full example of this at the end of this slide deck. We'll start with the easier one. This one is taken from the book, but the latter one is not. The reason I've done this is that where the book goes from this intro rod cutting example, it's not my favorite. It's very mathematical in nature, which is great for those with fantastic math background, but not so great for those who don't have such a great math background. So I think seeing something a little bit more applied would be better. But we're going to start with rod cutting. So let's introduce the concept of the rod cutting problem, and we can see how dynamic programming applies to this. So here we go. We are a company that buys long steel rods. I don't know why we are in this business, but all we have to do is buy long steel rods and cut them into smaller steel rods and then sell the smaller steel rods. So we're flipping long metal for chopped up pieces of smaller metal. And the fact that we know the demand out there for smaller cuts of metal tells us how to take this bulk metal and apply the cuts in order to maximize our profit. So the actual process of cutting a rod is free, but rods of different lengths have different values. So we take as input, we get a steel rod of I inches and a map of length price pairs. And here is the map we're going to start with. So this tells us, based on the length of the steel rod, how valuable is it? Just looking at this table for a second, what do we notice? What patterns do we notice within this? If you're optimizing this company for this, what overall takeaways are there?
The longer the rod, the more expensive it is.
Yeah,
Yeah,
okay. Every longer rod is at least the price of the one below it. Great.
That's definitely one of them. Something else is, the function's a little bit interesting too. Let's see how.
Thoughts?
Yeah. Going back, while price increases, I wonder if there's another variable into such as supply. And you have to see if say you have 10 units of length available, so 10 times 30, 300. But what if you split it to say just 24, you have a little bit more length to work with. How do you balance that out?
Yeah. Yeah, that is a very interesting question. In that, let's say you have a steel rod that's 10 inches. How do you want to cut that up? What does maximize the overall profit? We see that it's not immediately apparent, is it? We have some ideas that we can see that 9 and 1 is worse than 5 and 5, but there's no guarantee that we only make one cut to this. We could build this 10 up of 6 and 2 and 2. Or there's an arbitrary number of cuts in there to determine how confident would you be if I asked you to do this by hand that you had the perfect way of cutting this up. Yeah,
Sorry, I don't mean to interject again.
no, you're good.
Just doing a quick mental math. I think the optimal way to go about it is probably maximize on that blink 6. Double that, it's near 34, 32, so it's marginally better than that. So probably do better being able to stop on that.
Yeah, no, that's good. It's good analysis. We could leave it at a rod of size 10, and that gives us a minimum value of 30 that but imagine that we bought it for 30. Is there a better sequence of cuts that we could make that would make this more valuable than 30? So the output to this is suboptimal breakdown of lengths of metal that would allow us to maximize, given the input, the amount that the single steel rod that we had, what cuts should we make to maximize how much value we can get out of it. So how many subproblems are there? We have a rod of length 10. How many ways are there to break it down? You can give an order here, not a precise number, but how many ways are there to break it down? A lot. That's a good place to start.
Plenty. I don't know how many I could count here. Not in this case.
There's a way to visualize this mathematically. Anyone see way to do it? 10 factorial is a good guess.
Not a bad one, at least. I'm not trying to be rude.
It is a good guess. It is wrong, but it's a good guess.
Yeah.
How many positions are there to potentially make a cut? There are 9, yeah.
9, yeah.
A rod of length 10 is you can either make a cut, leaving yourself 1 and 9, 2 and 8, 3 and 7. There are going to be 9 possible places to make that cut. So now imagine our choices are make a cut there or don't make a cut there. Does that choice affect the choice at the next place we could make a cut?
Yes, I think.
Does not. The price will tell us whether it's worth doing or not, but regardless of whether it's worth doing for profit, it doesn't change the fact that we could make that additional cut. I make a cut at position 1, it doesn't change whether I can make a cut at position 2. It changes the relative lengths and the number of cuts that I've made, but it's still an option. So there are 9 positions where we can either make a cut or not make a cut. What does that tell us our function is for the number of potential cuts? You can either make the cut or not make the cut, gives us an exponential base of 2. There are 9 possible places. So if I is the length of the rod in inches, then there are I minus 1 potential places to make that cut. So in this case, 2 to the 9 for a rod of length 10, which is 512. So if we're brute forcing this, a single rod of length 10, there are 512 different ways to cut this up. How would we know which of those 512 ways gives us the most money? Let's start thinking about this. I'm going to give people a bit of a task to do. Instead of using something as long as 10, because that gives us way too much work to do, let's start with a rod of 4 inches. And go ahead and draw out every possible way that we could break this down and the cost according to this table. So we have a rod of length 4. Write out all of the possibilities. How many possibilities should there be if we've done this right? 8.
8, yeah.
Yeah. 2 to the 4 minus 1, 2 to the 3, 2, 4, 8. So take a couple minutes, work with people next to you if you like. And let's see if we can visualize what this problem looks like.
8 ways, me. Alright. So, 8 possible ways out of any of those ways. Great question. What do you think? But all the time, always you break.
One 1 inch cube. Break it down into a 1 inch on it. Do 1 inch pieces and go. Or 1 inch pieces.
Yes. Let's see it.
How are we doing? We get those 8 pieces, we think?
Does the 4 inch piece count without cutting?
Yes.
Yeah, that wrote that down too.
So we can make 0 cuts. There's one way to do that. We can make 1 cut. There are 3 ways to do that. Cut at position 1, cut at position 2, and cut at position 3. That's B, C, and D. We can make 2 cuts. There are 3 ways to do that. We can cut at 1 and 2, 1 and 3, and 2 and 3. And then we can cut at 1, 2, and 3. Anyone recognize a pattern from this? If you've studied combinatorics in a past
That's
class, does this
Admin.
look like a row of Pascal's triangle?
Not something I'm the most familiar with. Just
There is 1 way to make 0 cuts, 3 ways to make 1 cut, 3 ways to make 2 cuts, and 1 way to make 3 cuts. We're drawing out Pascal's triangle.
oh yeah, I remember now. It's so long.
That's the row. The sum of each row of Pascal's triangle is just 2 to the power of its row. 2 to the 0 is 1, 2 to the 1 is 2. 2 to the 2 is 1 plus 2 plus 1, 4. 2 to the 3 is 1 plus 3 plus 3 plus 1. So this just tells you the number of whenever you have a binary variable like this, and you can either make or not make a cut in each of these areas, it's going to align with the ith row of Pascal's triangle in terms of the number of places and ways that you can make those cuts. The reason there's a mirror between 1 and 2 is for 1, you're asking where do I make the cut, and there is 1 way to do that. Here you're asking where is the place that I don't make the cut. So I don't make the cut at 3, maps to I make the cut at 3, don't make the cut at 2, maps to make the cut at 2, don't make the cut at 1, maps to make the cut at 1. So they're just mirrors of each other. Which is interesting and cool to see. Probably get rid of Pascal's triangle at this point too, but. Given this breakdown, let's actually now write the cost of each of these. And we're going to see that some of these have repeated costs. So what is the cost of just a length 4? We have 9. Here we have 1 plus 8, that's also 9. 5 plus 5, that's 10. 8 plus 1 is 9. 1 plus 1 plus 5 is 7. 1 plus 5 plus 1 is 7. 5 plus 1 plus 1 is 7. 1 times 4 is 4. What is the best way to do this? 2 and 2 gets you 10, which is more than the cost of the original. So we could profit off of this length 4 rod by making a single cut at position 2. So that we would have a 2 and a 2. Any questions on how we got there? Just kind of a base case of breaking it down into, these are all of the subproblems of size 4.
Yeah.
The issue here is that the number of subproblems would scale exponentially if we were to go through this brute force process. Where do we see repeated work? When could we have already known the answer without going through and recomputing?
Well, let's see, repeated work. I see 3 bits of repeated work on the bottom, E, F, and G, and I see D and B are repeating too.
Yes. Yeah, when we have the breakdown of a size 1 and a size 3, or a size 3 and a size 1, or a size 1, a size 1, and a size 2, all of those are the same work. We could have just looked that up in a table rather than recalculating and breaking it down into its components. Because what is the optimal way to break down a piece of size 3? If you were trying to figure out how do we know that we leave this problem of size 3 and not further break it down, you could try to save work there as well. Is there a method to these values, or are they random based on this fictional market value? They're prescribed to show dynamic programming work.
Yeah.
Yeah, so they are fictional, but they're prescribed to show the value of repeated work.
I see what you mean, at least by this point. I'm not exactly very unfamiliar with dynamic programming.
So let's take a look at, we talked about where the repeated subproblems were. Is there a general function or rule that we could use to solve this? We don't want to consider every possible subproblem. I was hinting at it moments ago. This breaks down recursively. And we have subproblems in the past slide here that this becomes, let's break this down into 1 and the optimal way to break down 3 rather than the cost of 3. If we could figure out the optimal way to break down 3, then how many subproblems would we have? We wouldn't have anywhere near as many if we could break down a problem of size 4 into a maximum problem of size 3, like we do in B, a maximum of size 2, like we have in C. And you find that we have a number of subproblems based on the number of cuts that we make. And then we just need to optimize the value of breaking those down. You can imagine that by solving this subproblem 4, what we've done here is now whenever we see any rod of size 4, we never have to break it down further. We know that the optimal value is right here. So in some future problem where we see a rod of size 6 and we're considering a breakdown into a 2 and a 4, why repeat the work of figuring out how to break down this 4 and all of the possible ways we could break down that 4 when we already have the answer stored from the prior work that we've done? The value of size 4 is 10, without considering the exponential number of breakdowns of problems of size 4. The problem, if it were a 4, but if we wanted to break this down and figure out optimally, is 2 and 4 the optimal solution? Well, we know that there's a better way to break down 4 than just assigning it a value 9. We can assign it a value 10 by breaking it down further.
I get what you mean, sorry.
Yeah, so we'd be in some kind of tree where we want to say, given that we're at a problem of size 6, how do we break it down?
I'm sorry, I'm just asking questions.
Yeah, no, you're good. It's good for Good for understanding. But with this problem solved, we don't have to consider a lookup to just the value of a size 4. We could optimize and say, this 4 has a value of 10 because of its optimal breakdown.
Oh,
So we want to construct a solution to this entire problem that has us doing the minimum amount of work to figure out the optimal cut structure for an arbitrarily long steel rod. So there is absolutely repeated work done and work that can save us a ton of time if we intelligently come up with an algorithm and a way to store the work that we're doing.
right.
So there is no general rule we can follow that solves the problem without considering every possible subproblem, but we can optimize the order in which we solve those subproblems so that we can maximize the amount of reuse that we have. So if we solve it using dynamic programming, we end up with something that looks kind of like this. This should look reasonably recursive. We say if we're in a base case, if there's a rod of size 0, then if the query is 0, then we return 0. There's no value we can get out of no steel. If we don't have any steel, we can't get anything for it. We'll set a value to be minus infinity. If we're going to eventually find a maximum, it's worth setting this not to any reasonable value, but to minus infinity, because we guarantee that when we first look at the maximum of something that exists and something that is new, if we set the initial value of what exists to minus infinity, the maximum of those two is always going to be the first data point we consider. What is the maximum of minus infinity and some other value? It's always going to be that some other value. If you set this value to be 10 initially, then if the maximum value happens to be less than 10, then you return that initial value that you never want to return. So we want to set it as small as possible. So assuming we set it to the smallest possible value, we will then loop over and say we're going to either make a cut or not make a cut at each position, and now say that we're going to get the maximum of that cut and the cut that we had before as the new maximum. And at the end of that, we're going to return the best value that we got in terms of the overall cost of, I guess, the sell price of the cuts that we make. Question on the pseudocode? What's the flaw in this pseudocode? There's a very large flaw in terms of its usability. Yeah.
I'll tell you like what
It does not tell you what cuts to make. It just tells you the value. That's exactly right. Imagine that we pass in a 26-inch steel rod, and it tells you that the best we can do is $82. Great. How?
Yeah,
That's missing from this. So when we talked about that step 4 a couple of slides ago about storing the optimal sub solution, the subproblem solution, this is the path to get to that solution. It's one thing to be able to return the optimal value, that's great, but if we can't take action off of that optimal value, that doesn't tell us very much. So we need to store the path that we take when we write something to our caching table. When we're breaking a rod of 4 inches down into a rod of 2 inches and 2 inches, we need to store that that is the optimal way to break that down. So that when we come up with, if we're going to use a portion of our subproblem, it tells us how to do that. So in general, how many calls to cut rod are we making from this? If we pass in a P and an N, we're going to need to make this call for every I possible cut for each possible sub size of this. So it ends up being exponential. Even though this loop only happens one time, that maximum, we have to consider every possible cut or not cut for every possible rod size from 1 up to n. So if we're asking the 10-inch rod question, then we're setting for 1, 2, 3, 4, 5, 6, 7. But when we're considering rods of length 7, we have to figure out where to make that cut and break that down where everything else is a lookup. So it's still exponential with respect to the rod length. And a good question might be, if we're doing this and we've set it up as a dynamic programming problem, but we're not yet reusing our subproblems. If this is exponential, what do we think? At what value of 2 to the I minus 1 are we starting to have a noticeable runtime effect? Knowing that computers can do something like a billion calculations per second, but not all of these are one CPU cycle calculations. So you can anticipate we have maybe 10 million of these that we can make per second. When does it start to become noticeable in the calculation time of rod cut? At what rod length, approximately, do we have 10 million calls to this? Basically, 2 to what power? It's about 10 million. 10 gives us 1024. 20 gives us a little over 1 million. So it's about 23. As soon as we have a steel rod of length 23, it's going to start taking us a second. 24, 2 seconds. 25, 4 seconds. 26, 8 seconds. 100, you're going to be fired before it returns an answer to you. In fact, you're probably going to be in a casket before it returns an answer to you. So this is useful, but it doesn't scale well. So that's bad. How long would it be before the sun expands into a red giant boiling off the oceans and enveloping the earth? It's surprisingly not that high. By rod length 150, we're toast. Really, by rod length 70, we're probably toast.
Wow.
So
is a lot.
Yeah, this does not scale well at all. And so for a problem where we recognize the subproblem structure like this, we need to incorporate storing and reusing subproblems, because this starts to scale at a level that very quickly becomes useless to us. So as a recurrence, we can figure this out. It takes us one operation to solve a problem of size 0. This makes sense. We just return 0. T of n, on the other hand, we need to figure out 1 plus the sum from all j is 0 to n minus 1 of t of j. This gives us the subproblem structure. And if we solve this recurrence with the substitution method, we find an exponential complexity, which maps to what we expect. Person online asked, we're probably not buying 50-foot rods, though. It's like, depends on the profitability. I will buy as long of a steel rod as I need to in order to make a good profit. I'd like to be able to know that, and I might be able to get a competitive advantage over my technologically useless competitor if they implement this without dynamic programming, and I implement it with dynamic programming. I will make so much more profit, I will drive them out of business. All right, so what would a tree look like for this, for brute force rod cutting? It looks very similar to the Fibonacci sequence of rod cutting. We have a rod of size 4, and this breaks down into, we need to solve the rod of size 3, the rod of size 2, and the rod of size 1 subproblems. The rod of size 0 is a base case that returns a solution for us. But you see the amount of rework that we're doing when we do this recalc. It looks very much like the Fibonacci tree that I drew for the Fibonacci example. How many times are we answering the rod of length 2, the rod of length 1 question, the rod of length 0 question? There's a lot there. way more than we need to if we could relate this tree as such and cut off everything else other than a very fast depth first search in a way that would look like a bottom-up calculation. You can imagine that if I had optimized a 0 and a 1, we already know those are lookups. A 2 is either 1 plus 1 or 2. And since we already know what 1 is, that's a lookup. Once we optimize and figure out whether it's better to leave a rod of 2 inches alone or cut it into 1 and 1, then we can use that information to look up 3. It breaks down into 2 and 1, 1 and 2, or 3 and 0. And all of those at this point are just lookups. And now when we are looking at a rod of size 4, we can decide to break that down into 3 and 1, or 2 and 2, or 4 and 0. There are only 3 ways to break that down, assuming that the orders are the same. And so we can ask the 3 subproblems for 4 rather than recalculating all of this work down here that we save and become lookups if we do this in a way that mimics the bottom-up process. Any questions on that? I get in moods when I write these slides.
Really?
In case that's not apparent. So to use dynamic programming, what does that actually look like to implement? So we talked about what it would look like to write it with dynamic programming, but now we need to actually store the subproblem solutions. So we should be instantiating some kind of data structure that is going to store the optimal subproblems for us. When we figure out how to break down a steel rod of size 3, then we should store that information. Whenever we have a problem of size 4 can break down into a 3 and a 1, the breakdown of 3 becomes a lookup rather than a recalc. So when we go to solve an unknown subproblem, we're going to look up and say, have we solved pieces of this subproblem before? Only do the work to calculate what is an optimal subproblem for a subproblem we haven't seen before. If we have seen it before, then it should be in our table. If we have to go resolve or just solve a subproblem for the first time, the last thing we should do is write that into the table so we never have to do that work again. So let's take a look at what that would look like. The top-down solution versus the bottom-up solution. The bottom-up solution is probably the one to start with, just because that is very intuitive to think of to solve a subproblem of size 10. Let's solve subproblem of size 1, then a subproblem of size 2, then a subproblem of size 3, then a subproblem of size 4, all the way up to 10. By the time we ask the 10 question, we've solved all of the possible subproblems that we could reasonably ask. So they all become lookups. So you're just going through one loop from size 1 up to size n, and as a loop in between, underneath that, you're going to do a bunch of lookups for if we make or don't make the associated cut at each one of those positions. What are the possibilities? There are only going to be j plus 1 possible possibilities for that. So this becomes significantly more efficient. Even though it looks like it's more code, the actual number of calls to this are significantly fewer. And the top-down solution is going to start with the problem of size 10 and break it down into all of its subproblems, throw all of those subproblems in a queue, and start with one that's then going to break down, then break down, then break down. It looks like the tree from before, but we're basically doing a depth-first search on that tree, where to solve 4, we need to solve 3. To solve 3, we need to solve 2. To solve 2, we need to solve 1. To solve 1, we need to solve 0. 0 solves itself. 1 now solves itself. 2 now is a lookup. 3 now is a lookup. 4 now is a lookup. And we're done. It almost looks like bottom up as a process.
I see where you're going.
Because we don't have to do any of this work. All of this work is already stored in the table from the first time we did it. So that's the only thing with the top-down solution. We're just going to break it down into those subproblems. Some of those subproblems are problems we haven't done before, and by the time we return to this level of the recursive tree, then what we find is that the remaining subproblems have already been solved by the work we did to solve the first subproblem, because we solved it in that depth first search order. So two different ways to implement it, but both of them end up running in the same amount of time now, because we are avoiding those subproblems. I'll spend a little bit more time just kind of looking at this, I think, because it's worth just looking at why this works. Let's map this code, this pseudocode, to the idea of breaking it down.
Is it supposed to say memorized or memoized?
Memoized.
Memoized. That's a new one.
It is memoized.
Okay, I'll roll with it. So that is interesting and cool.
So let's stare at this for a little bit, see if we can come up with an understanding of exactly how this is working.
Well, a new array is created to start with. Then it calls the more, I'm not sure if I should say more private, maybe. But let's see.
Instead of doing the nested loop that we have in the bottom up, we basically have one of those subproblems. This is the outermost loop. This outermost loop in this method is the same as the outermost loop in the bottom up solution.
Why would the negative infinity though? That kind of confuses me a little.
In what sense?
Just like why would you use that for an array like that?
Oh, the 0:n being that's a discrete style list.
I suppose, okay.
Because we don't want to attach ourselves to the syntax of any particular language, because then it's only readable if you've studied that language.
Got it.
So we use a more mathematical way of writing pseudocode in books like this so that it is language agnostic.
All right. I suppose I'll just roll with it then. Thank you.
There's a great question on Zoom about whether, since this ends up being basically the same efficiency, why would we bother to think about this from the top down? It seems like it's the same thing as bottom up, just with a little bit more work in it. And it boils down to the same reason why some problems are better when you write iterative code. Some problems are better when you write recursive code. If you are solving something bottom up, by nature, it is iterative. If you're solving something top down, by nature, it is recursive.
I see your point.
So if we look at something like the Tower of Hanoi recursive problem that is so much easier as recursion than it is as iteration, then it would actually be more efficient in terms of how long it takes us to write the code to write it top down rather than bottom up. If you instantiate that bottom up, then you're responsible for the stack. You need to make a stack. You need to figure out what's on the stack. There are potential bugs with using the stack. And the call stack for the recursion is your stack. So it's already been instantiated. It is bug-free by the nature of it being the call stack. You just remove the complexity of the stack from the problem in general. So in this case, it looks way more efficient and easier to use an iterative approach, and it is. It's not necessarily more efficient asymptotically, but it's more efficient in terms of the lines of code that we have written. But both are valuable, and both will look easier depending on the problem that you're solving. But that is a really good point to note and observation. How are we going? Does it make sense that the auxiliary method here is just the inner loop from the bottom up? It's doing basically the same thing. It's doing some setup in the same way that bottom up does some setup, but then goes into finding the maximum of two things. It just ends up being a call to itself here when we go down and make subproblems smaller and smaller and smaller so that we can find the optimal solution for a particular length. Once we know the optimal solution for that particular length, we're going to write it in the table, R of n equals Q. And when we do that, then we see that that becomes the lookup that we can then use when we say Q and P of I, that's saying that P of I may already exist in the table, so we can look it up. Rather than go through an entire recount. Okay, we see it later on. All right, we're out of time already.
Wow.
So we're gonna have to come back to this tomorrow. That'll be our last day before we dive into a bit of review for the upcoming exam. None of this is going to be on the exam. Keep in mind that only topics that are on the study guide will show up on the exam. So we're covering material that'll be on the next exam. I have office hours starting now. To the extent to which I can be helpful. Sorry. The next one after this one will probably be about 3 weeks. I'm anticipating exams at this point being weeks 4, 7, and 10. I hope I can have that. 3 total.
And you said the first one or the last one?
Yeah, just due to the nature of the material that we cover. There's one more section that is similar to this when we talk about incompleteness theory later on, of course. But most of everything else will be more about